Can you send me, did you see the email? Can you send me an email?
I didn't.
I think you emailed
About 7:30 or so. Yeah, I can look in here now though.
Yeah, well, whenever you see the email, the next time you look in the emails, you'll see it and you can.
If I don't do it now, I won't be able to do it until tomorrow.
Yeah, it's perfectly enough, but no, there's no deep rush forward, so there's no.
Yeah. Yeah, okay. Okay, so you got all this time.
I guess I'll watch the news and get the press.
Yeah, there's something about the news these days.
It's exciting. One episode has a political novel. I like political novels. I think they're fun. The maneuvers of political movements.
Just for one time I went to Hong Kong with no baggage other than what I could fit in my pocket. And when I went out for lunch, when I came back, it was the hotel manager. We thought we were dead or kidnapped because there was no luggage.
A good way of getting paid.
Yeah.
Good morning.
Hey. Good morning.
Good. PayPal. You said you PayPal.
Did you say you were going to
I'm actually setting up PayPal.
Or is that
You don't need it. You don't need it.
No, but I do want, I have independently for completely separate reasons to set up a PayPal account, which in fact is something I should have done.
the six from our little group that are there, so it's just kind of nice. Not very often we can get together.
No, I know how it works. The PayPal will be the best way for me to do it.
Maybe a little early, the website is like, I actually registered yesterday, it's just because it was there, so you can tell it. I think it's the first week maybe, I forget.
That's next up.
Hello, Sam.
Yeah, 2019.
Good morning. Good morning.
Good morning.
You're welcome. You're welcome.
Who's chairing today?
You should share yourself for protection.
That's a point, who is? Maybe Lou? I don't know. Anton, this chair.
No, I'm talking as well, so Peter, can you do it again?
Yeah.
That's all right.
Keep you under control.
That nuisance being good at something, isn't it? And you end up having to do it all the time.
Yep.
Yeah, I did try and send a message, Roger. No, I wasn't able to send anything anyway because I'm still in Southampton. I wouldn't be able to get there. But yesterday, I was just absolutely shattered. I was just so tired. Really couldn't. No. Well, also, I did have a lot of stuff to catch up with on
This is kind of that'll work.
It wasn't until ANPA that left me shattered, it was the previous 3 months. I really wanted to have a chance to have a few more words with you and Louis about that.
If you really don't have to go to Bristol, I can take you home and look after you for a little while and you will feel a lot better.
Alas, I do have to go to Bristol, I wouldn't have
By the sea, nothing to do, excepting some of Nina's lovely food.
That would please go.
You've got to do it, you've got to do it.
Maybe I can take you up on that later in the month.
There's a free seat in the car, so you make a phone call to Bristol.
This has 10 gigabytes.
Oh yes, that's more than enough. That will fit on that very easy. I'll do it now. No, that's great. That's fine. We'll have to have a chance to talk. Now I have been you might be going straight back to Glasgow after this.
we have a tent and we have a plan. So the plan is that we'll drive until we fall over and then jump in the tent. So when we fall over,
A very sensible way of doing things.
Baldrick had a plan as well. Cunning one.
This is not a cunning plan, though. It's a simple plan. Good.
Also, unlike Baldrick, it sounds like this one would work.
Okay, when are we starting? You waiting for anybody?
Hang on. Oh, yes, Nicola.
Nicola's not coming.
She's not coming.
Oh, she's not
She's gone, she's gone.
She has to go. She has.
Oh, I am sorry.
Yeah, it's a family wedding.
Oh, that means my gosh, I have to goodbye for that.
Yeah, that was the cake stuff. So,
Ah, yes.
Yeah.
Can you just give us a second?
You missed out on making marzipan. She was asked
Let's
for
move
it.
that.
Yeah, I remember. Oh, well.
so much this way. Yeah, that.
I'm sorry, is everything okay? Yeah, but you, okay. Should be no falling.
Some people's minds are so lofty, they're always looking up, you know.
That's the drama for today
I-
now.
that's right. I hear who's blocking the view.
We haven't heard the speaker? Speaker disappeared?
We are speakerless.
Speakerless.
Oh, here he is.
Okay. Everybody set up and ready?
Yes,
Okay. Okay, John?
Ready?
So our first speaker this morning is John Williamson, who's going to talk about the emergence of physical mass, field spinners, and a new theory of light and matter.
Good morning, everybody. This is a new theory, I think. I'd be very pleased to hear if anybody has played around with any of these things as well. But the theory I'm going to present is one. It's always been my conviction that nature must be at its root very simple. And I know it has to be simple for me, because if it's not simple, I'm not really truly going to understand it. So what I try to do is I try to take things down to the very bone, see how far you can go, what's left, how far can you strip physics down to give something which will build up into something which describes a large part of it. So I'm leaving myself freedom, I'm going to leave myself freedom, but I'm going to try to always complexify things, but I'm going to try and keep things as simple as possible at the basis. And the idea comes from computer science, from process, that by taking the simplest possible process elements, one builds the most robust software and the most robust way of doing things in a software context. So now, this is part of an ongoing project, mostly run by myself and my good friend Martin van der Mark, who was at Bicycle, who was at the Vigier conference. And we've been working on this for over a quarter of a century, in various guises, trying to understand how stuff works. But many other people have been involved, and their names are up here at the moment. Some of them you may recognise. Tony Booth is up there, for example. He's helped at one stage and another. Other people are now dead. Hendrik Casimir helped us at one point when we were looking at the early stage of our theory, looking at confinement mechanisms for the self-confined mechanisms for the electron. We worked with him. That was a great pleasure. Ulrich Enz was another great physicist who is the father of the soliton way before Higgs bosons and so forth. Enz was working on solitonic theories, and I can thoroughly recommend his work as well. Although it's pretty old now, back in the 40s and the 50s, it's still beautiful science. These two are no longer with us, I'm afraid. Most of the others are. Also, there are a couple of societies I belong to. The Quasical Society is one I started myself, and it consists of a lot of the people in this thing. There's also something called the Fanaten, which means the fanatics in Dutch, and we have a bunch of fanatical physicists, most of whom are young fanatical physicists, who meet every 3 weeks at somebody's house. And what happens is, people make up whatever they'd like to talk about, somebody else hosts them, so you have a host and a speaker. The speaker speaks for a long time. We don't give ourselves any limits, usually about 3 hours in total. Not talking, but for the total thing. So it might maybe have an hour and a half talk, and then we'll sit down over beer and coffee or whatever else and just discuss whatever comes up, which is usually about the talk, or could be about anything at all. And it's been going for 25 years, this thing. So whenever I'm in Holland, I try and go along and give a talk, or at least go along and listen to these things. So these are other societies other than the one here, which are vibrant and alive and have lots of young people in them. So, where I want to start? I want to start with physics. I strongly believe that physics has become mired since about 1950s. It's become mired in its own complexity. It's become mired in a situation where people get used to not understanding aspects of physics. They get used to saying, okay, that experiment doesn't really fit with my theory, but I'll park that for the moment and I'll work within this tribe of physics where that kind of idea does work. And where it's really stuck, I think, is in theories that can't be calculated with. If you have a theory where you can't start from a priori and do a calculation and get some prediction, which can then be tested by experiment, which can then be falsified true or not, for those theories, the scientific method itself fails to operate. And these theories cannot be knocked over in the usual way. And this includes any theory which has something in it like non-perturbative. Non-perturbatives means even the most powerful methods we have mean you can't calculate stuff with it. You can do things with some of these theories, and many of these theories have very nice features, but you can also get yourself wrapped up in the theory and not move outside it and not be able to take things forward. So I think the new generations of scientists coming into science have tended to work in a small part of science and have got used to not understanding the mysteries of quantum mechanics or the depths of the way the Big Bang happened and inflation happened after that, and or string theories or quantum chromodynamics. They get used to not understanding whole areas of physics, and that's thought to be okay. Now, I don't think that's okay. I think that if you don't understand something, that's an opportunity to learn something. So, but I have a stelling. Stelling is a Dutch thing that one puts forward. My stelling about the whole of science and about anything else is that if something sounds pretty ridiculous, it probably is ridiculous. And there are a lot of things which, to me, are at the root of present-day science, which are just ridiculous. I mean, just total nonsense. You wouldn't believe it if you were a child of 5. They don't if you try. Just try it. It's a good experiment. In the beginning, there was absolutely nothing, and then suddenly there was this enormous explosion. The universe came into being. Now, if that wasn't the Big Bang theory, that's pretty much the standard theory of how the universe began, that would sound pretty ridiculous now, wouldn't it? So, now, taking... Pardon?
Most creation didn't start that.
That's right. But
Creation myths.
myths. But some myths are better than others. Some of them have got sexy stuff in there. They've got nice bits in them. This one's just boom. So anyway, never mind. Anyway, could be. But I think that what really has fallen out of fashion is clear and rigorous thinking. Taking something where one takes all of the starting points, looks at them very carefully, puts everything together with that and takes all of the consequences and looks at those consequences. Those consequences don't fit. You don't just pretend that's okay in some way. You go back to the starting point, throw the theory away and try and start with something else which is going to give you something that fits.
Can I quote you on that?
You certainly can. Thank you. So, any theory that disagrees with certain aspects of experiment is now somehow deemed to be okay, provided you're kind of far away from that stuff. And I don't think that's okay, because I think that means that you have a lack of understanding. One has a lack of understanding about that. It's an opportunity to try and fix it, or it should be in proper science.
So in some sense, Occam's razor got inactivated.
No, but Occam's razor is a different thing. Occam's razor is saying that it's the simplest. It isn't necessarily. The universe doesn't have to be the simplest possible, but it would be nice if it was, of course. But I think that's the best place to start. But it's not the Occam's razor. It's the cycle of science. It's the scientific method, which is the powerful thing that got us to the quantum electrodynamics at the beginning. Having said all that, physics as it stands, the physics we have, is nearly completely correct in all details. It fits so well with so much of science, so much of nature. Is that readable for everybody?
Yeah. Yes. Yes. We need to focus is better.
Let's get the focus.
Yeah,
Let's make it a bit
Yeah.
bigger.
That's a lot better. That's much better. Thank you. Okay, I have another version of this with bigger, larger type. It's got more slides. So there are lots of excellent practical theories that you can calculate with, you can do stuff with, starting with the most useful of all, which is Newton's laws, which is classical mechanics. That's what nearly everything you see around you. That's what car works on, pretty much. At least an old car, the carburetor. That's pretty much all classical mechanics. That's all you need to make things fly, to make things go fast, to make things go around corners. If you want to get a bit fancy, there are other ones. The other one that's important is Maxwell electromagnetism, which is pretty much what we use when we're designing high-speed electronic communication stuff. You don't usually bother with quantum electrodynamics when you want to design a resonator. Although quantum electrodynamics is another one of the good ones, which you can really calculate stuff with right as many decimal places as you like. I played with this stuff in my youth. I wrote programs to do this. I've done it a lot, and you do get the right answer all the time, which is very, very satisfying, especially when it's silly stuff that us nerds like with 6 decimal places where experiment agrees at that level. Wow, this is cool stuff. That's fantastic stuff. So there are lots of really good things. There's quantum mechanics in many guises. I've been using quantum mechanics now for the last 25 years. When I first came to physics, quantum mechanics are used to think about and imagine quantum transport devices. You imagine these things, and then some clever person goes and builds them, and the next thing you know is you've got 3G mobile phones wandering around, and the government sold them for £30 billion, and not given the people who invented the original technology a penny. Manna from heaven. So this stuff is the stuff that causes and creates the world we live in, and it's a magnificent edifice of utterly beautiful, beautiful thinking of many, many minds. So though I think that some aspects of science are mired, something is mired, I think that the present situation is extremely good. And if one looks at the edifice of science as it stands, anything you try and do to it had better agree with all the good stuff. It must absolutely fit in, click, click, click. Otherwise, you're almost certainly on the wrong track. So for anything where the stuff is properly experimentally verified, where the scientific method has operated, which is pretty much up to Feynman's quantum electrodynamics, where it began to get a little bit flaky, because well, that's perturbative, you can calculate with it. But any new theory one comes up has to either encompass what's gone before, or extend it in some way which is consistent with the bits that you want to keep, which is most of it, or derive its starting points. Otherwise, you're probably on the wrong track.
So would you say that you would need to make sure that whatever theory, whatever new encompassing theory, it has to not only reproduce the original decimal significant figures up to
It has to
create even more?
No, not necessarily, because in the realm of some of those theories, general relativity and quantum electrodynamics, there is nothing to extend at the moment. There's a little bit of a thought there might be a sort of 5 standard deviation effect right at one end of QED, which is very interesting, but really, most of the lattice really cannot be extended, so it just has to reproduce it. At the moment, I mean, we just can't do the experiments. I mean, in the future, we may be able to do so. So what I'm going to do is I'm going to propose a ridiculously simple new theory with only 5 elements. No nonsense with lots and with E8 or zillions of different kinds of starting points. I'm only going to put 5 things into it and take the consequences, see how far one can get. And the 5 things I'm going to put into it are space, time, and a sort of stuff, which we're going to call root energy, square root energy. I'm going to put a square root substance into this, and I'm going to let it play in the dimensionalities of space and time. Now what I said isn't quite true. Those are the elements I'm going to put in. That's the starting points, which are like the atoms of the theory, if you like. But I'm also going to put in a mathematics. I'm going to develop a mathematics, which is a very specific mathematics, which is designed and is under design, because this is not a finished project. The bicycle project has to do with this, which is being designed to parallel as closely as possible the elementary processes of nature. So what happens in nature is the basis of is filled into the basis of the mathematics, as far as my meagre talent enables me to do so. However, I know that when we're doing calculations of this, they very rapidly get very complex. So what I have as a project, especially Innes Morrison has been writing a program which enables different sets of parameters. You can change the handedness of bits and pieces of the algebra. You can change the ordering in which you do stuff, which changes the sign in non-commutative algebras. You can put in multiple orderings. You can put a series of switches in which allow you to change the basis But then it also does calculations. It does calculations that used to take my monster calculating friend Martin a week locked upstairs in his loft to do, and he'd used 2 block notes of paper to do so. I can show you them now, they're milliseconds on the computer. So you can do this stuff and you can have a look at how that stuff runs through all the stuff, and then you've still got to, it doesn't do all the work for you, you've still got to do a lot of thinking, but I'll show you some of that later if I have time. We're going to propose a new theory with 5 elements, space, time and root energy only, and see how far it goes. Now, because I only propose 5 elements, I've got lots of freedom to let other things in, and you'll find the algebra I come up with is a reduced Dirac algebra. It's the Clifford algebra CL13, so it's sometimes called a real Dirac algebra. It isn't a Dirac algebra because Dirac algebras are more complex, both in terms of being complex and also literally. You can see all the other Dirac algebras as being a complexified Clifford Dirac algebra. So what I'm going to do is I'm going to look at, in Peter's terms, I'm going to look at,
That's what we're doing.
yes, I'm going to look at 5-term, sorry, I lost this. What was I going to say? Where was I? I'm going to look at I'm going to look at I forgot what I was going to say, and I lost it. It doesn't matter. Okay, right. For what it's going to do is, I'm going to end up with a theory which mathematically, I'm not going to say physically, because putting the physics in is another thing which has value and has judgment, but mathematically it encompasses Maxwell's theory. It provides an extension of relativistic quantum mechanics. It brings the mass in. I bring the mass in what I think is a more sophisticated way, at a deeper level. The rest mass, so it extends relativistic quantum mechanics, and it derives the starting points of quantum electrodynamics, including the point-like nature of interaction, the value for the fine structure constant, an equation relating the fine structure constant to the Planck constant, the charge. I'll derive the charge. So it gets the charge. What it doesn't get yet is the mass. So the parameters of quantum electrodynamics are charge and mass that one renormalizes to doing these theories. So that's what's going to come up, and what I've decided to do. But it's also I'm also going to show a wave function which is a fully relativistic photon wave function. The new theory is also capable of describing not only matter and charge, but also light, because it is an extension of classical electromagnetism and of quantum mechanics. Well, sorry, it encompasses classical electromagnetism and it extends relativistic quantum mechanics. So I'm going to do the entire talk in 5 minutes, then I'm going to come back and fill in the details. That's the plan. So the basis idea, the thing that started me on this many, many years ago after I finished my undergraduate degree, and having finished the last paper, couldn't actually stop doing physics, so went and sat in the library for a week reading everything I could find by a chap called Bone, David. Beautiful, beautiful stuff as well, underdrawn. Was I came to be convinced that the nature of light and matter was not different fundamentally. Why? Because of the existence of processes in nature, such as electron-positron annihilation to 2 photons, or photoproduction of matter using light, which is in quantum electrodynamics, what you do is you look at photon-photon going to particle-antiparticle pairs. What I was looking for was a theory which would describe that process, the actual quantum mechanical process of moving from a quantum mechanical photon to a quantum mechanical electron. Now, there wasn't such a theory, and there isn't such a theory, except for the one I'm just going to show you. So, at that time. So, but then the thing has been a search for something which can describe that process, and that's the Classical Society's mission. So here we are. So the question is, how do the electron and the photon, for that matter, how do they combine themselves? How do they work inside? What's an electron? How does it work? How does quantum mechanics work? What's waving and what's it waving in? That's the question. And it comes from production and annihilation of charges. How does energy wrap up into matter? How does it form? What is it? And the basic idea is this one, which is, does anyone have a pointer? I'm sorry, I'm a bit but the basic thing is the big blue and green thing here. What we've got here is the 2 straight line things coming in are, red stuff is momentum direction, green stuff is electric field, and the blue stuff is magnetic field. So these represent 2 circularly polarized incoming photons, left and right. And then the loops represent an electron with the electric field pointing everywhere inwards. That's the top loop is an electron loop. And
This
the bottom,
on the back.
so this is an incoming photon, this is an incoming photon. Twisting electric and magnetic fields through space, it's circularly polarized, so it's spiraling in. They interact in this region, and then what happens in this region is the photons mix in such a way that they formed where one was going right, and the other was going left, left. They now go left, right. Sorry, one goes left, right, the other goes right, left, and they end up mixing with one another to form something which is a circulating, self-sustaining system, an electron and a positron. So that's the basic idea. Now the initial stuff for this was published in a 1997 paper of Martin and myself. So this idea, this conjecture as it was at that time, because we conjectured that that could happen, we didn't have a force, we didn't have a confinement mechanism, we didn't have a theory. We just said, what if it does this, what are the consequences? So we postulated at that stage that happened. That what's happening is that a boson pair, equal and opposite spin, curls up into two double loops of a fermion-antifermion pair, conserving charge, zero charge to begin with, zero charge at the end, spin, etc., etc. All of the numbers are conserved, of course, because the process is a physical process. So that's what we did then, this stuff. And we could do some, when we did that, we could do some calculations, including calculating the electron charge from Planck's constant. So that was the 97 paper, and that's a semi-classical paper. No proper theory in it, although we did have a look for confined mechanisms. And we went around and talked to people like Casimir to try and find mechanisms by which this might happen. We couldn't come up with one at the time. So I'm going to rectify that deficiency now and show you where the force comes from that makes the electrons go round and round in circles. So it makes the photons go round and round in circles and hence form the electron. So how are we going to do that? Well, I'm going to extend Maxwell's theory. This is Maxwell's theory up here. Maxwell's theory can be written in a compact form using a 4 derivative in a Clifford algebra, d mu, which is a relativistic derivative. That's this thing just here. What that is that's d by dt minus d by dx minus d by dy minus d by dz. It's a 4-vector derivative. But there is something which is going to go into this, which is that I'm going to use something which I call absolute relativity. I'm going to sharpen the principle of relativity to mean that I'm not going to allow anything to happen in the algebra unless it's accompanied with its proper unit space-time, space or time vector. And that's going to include the maths I use to describe exponentials. I'm going to be utterly ruthless about this and put the stuff in where it should go anytime, or it's not happening. So if I can't do that, then the theory is not good enough, and one will have to change things. And that has happened many times over the last 20 years, believe me, when we've looked at some of the edges of what we're trying to predict. So at the moment I don't know of such things, but if anybody can fill me in on one, then we'll have to start again, won't we? So this theory is not just perturbative, it's analytic. So it's utterly naked, it is bare to experiment. So what is it? Well, that's d mu, I've written here as d mu gamma u, that's the 4 derivative of the 6 field, that's the tensor field, ex, ey, z, bx, by, bz, gives you in a single step, and I'll show that shortly, all 4 Maxwell's equations with the correct sign. I'm going to extend that, to extend this object here, to a more general multivector within this Clifford algebra. Instead of just taking the field-like terms, I'm going to take the other 10 terms. What are the other 10 terms? Well, some of them are just what you'd like to have. There are 4 terms which describe a kind of current. There are 4 terms which describe angular momentum. And there are a couple of terms whose subalgebra is isomorphic with complex numbers that describe an invariant mass. So that's the terms that we're going to get. And then when you do that, you get this equation, which I'm going to go into more detail later, so as well as electric and magnetic fields, E and D here are the electric and magnetic fields, they're written in a very simple form. Extra terms are going to come in, and the extra terms are down here. There's 4 new. So these are the 4 Maxwell's equations with some extra bits. There's my divergence of E term. Here's my time derivative of E and my curl of B, but there's an extra gradient of this P thing, and there's an extra dP by dt here in these terms. So extra terms come in. The P's and Q's are rest masses, but they're root rest masses, they need to be squared and integrated over like the field given energy. So these extra terms here appear in the Maxwell equations. The first 4 are the extended Maxwell's equations, and the second set of 4 are a set of 4 coupled differential equations which are coupling quantum mechanical spin to quantum current. There's a set of coupling equations between current and spin as well, which may or may not need to be satisfied at the detail level. So that's the set of equations that I'm going to abstract from to show where the forces come from that confine self, that can be self-extend itself. So this particular one here is P is the scalar term. It acts like the number 1 in Clifford algebra. That in things isomorphic to Clifford algebra, it's not quite a Clifford algebra because it doesn't. It has a unit scalar, but that unit scalar is different from the number 1 or from the mass. I'll show you why. And that thing this term turns out to be the thing responsible both for the nature of charge and quantum electrodynamics, for the coupling between field and charge and electrodynamics, and for the self-confinement term which allows the field part of the stuff to self-confine itself. It's called a pivot because it turns stuff. It's pivoting in conjunction with the electric field. It acts as a pivoting thing. So there are only 5 elements to go in, and I'll show you how that happens in the rest of the talk.
You assign the photon mass?
Pardon? Yes, it's 0. It's massless. Not only that, I can write a photon wave function which has exactly that property. It's rest massless.
But not momentum massless?
Oh, can be. At 0 momentum, it has 0 mass. At any other momentum, if it's confined, it has the mass due to its energy, and that confinement is Martin showed. Now, so this is the quantum bicycle project. Quantum bicycle, I couldn't use quantum bicycle because some guys in Australia make bicycles and they call them quantum bicycles, so there you go. So I had to shorten it. I shortened it to quicicles, so that's what this is. And I think if you set up a mathematics, you're setting up a system, a Wittgensteinian system. Some people call this Gödel, but I think Wittgenstein predated Gödel by about 10 years with his Tractatus Logico Philosophicus. And any logical system has boundaries introduced by that logic. So maths can enlighten you, and you can do stuff with maths. You can think in maths and think things that you otherwise couldn't think about at all. But it can make you blind to things outside of its scope. So you're both putting on binoculars to be able to see more clearly, but you haven't seen the elephant which is charging down from the side because you've gone. So you're doing something which expands your understanding, but at the same time you're self-imposing constraints, and you must be aware of this. So what I want to do is bring physics into the maths at the process level and forge a theory to describe single quantum particles. So I want to find that axiomatic basis which best parallels physics as I know it when run through the operation of doing the proper and after you've done a lot of work to actually calculate through this stuff. The first time I presented this theory, Michael was present. And I had a sign mistake, which I didn't know about, I was thoroughly ignorant about, which I've found since. And so this is a slightly different version of the theory to the one I presented in Marseille at a high-energy physics conference a few years ago. It takes that much time to really run through all the maths. But the current theory has new solutions. It has photon solutions, which I don't think I might have had then, but and it has physical spinor-like states, which I'm going to show how they arise. And quicicle has, as I said before, an international membership. So what I'm hoping is that the new paradigm of thinking, the new maths of thinking, allows one to think really into materials in a way, and systems and atoms in a way that otherwise has hitherto been impossible, because you can think into a composite system of light and matter. Now, you don't have a theory to do that, so even if this theory is wrong, and I think it's wrong, because I think that, I'll tell you why later, I think it's not the whole story, but I think it still gives you a platform to start thinking into things and into areas which involve the interaction of light and matter, such things as the quantum Hall effect, as fractional quantum Hall effect especially, such things as superconductivity that will allow one to design the materials and devices by thinking into them, how they work. How does, for example, superconductivity work? At the moment, the theory is rubbish. It's just like two quantum mechanics stacked on top of one another. It's not very good at all. I can do much, much better, because the coupling between light and matter there is strong. And so I think this is...
Sorry, John, was the fractional quantum Hall effect one of the things you had in mind when thinking about your second point, which is second bullet point here, which I think it's extremely
Yes.
striking, provocative.
Yes.
Yeah, because
It
it's
is.
precisely
Yes.
yes, the Hamiltonian.
Yes.
The way one has to think about mathematical systems in the Hamiltonian form is just clearly doesn't seem able to capture that.
Many conversations with these people, because I was at a top level, so I was giving keynote things at conferences. Any paper, if FizRev was phoning us up saying, when's the next paper coming? So at that stage, we were talking about this stuff with Halprin and Laughlin and Buttiker and all these people. So yes, it is inadequate.
Yes.
So part of the development, Lagrange and Hamilton is the whole story. Lagrangian field theory is magnificent, but that's what I said before. Maths can set you free, but it can make you blind. And as soon as you think everything has to go through a phase, principle of least time, principle of least action, principle of least phase, you have inserted a smaller brain into your head because you've forced yourself to think in terms of a single phase. And that is absolutely beautiful because it means you can calculate stuff, but I think it's a very dangerous thing to do because I think you've lost the dimensionality of the way that things really work to fit together, which is a quantum bicycle. It's cogs and gears, it's wheels within wheels, 3 times at least and probably 4. And if you've only got one wheel and no saddle, you're not going to get very far on your theory, which is pretty much how I would view Lagrangian field theory.
How do you push it forward without Hamiltonian and Lagrange?
Pardon?
How do you push things forward without Hamiltonian and Lagrange?
Exactly. I'm just going to show you.
Okay.
But the thing is that those methods are not poor. What happens is when you take the edges of this theory, you get bunches of new Lagrangians coming out, which you can then use to do new stuff. When you understand what the Lagrangian is, then we have another paper which I can give you, which Martin's sitting on because he doesn't think it's quite perfect yet, and he's first author and he's a perfectionist, but I think it's good enough, it should be out, which shows how from just the structure of the algebra you can generate a lot of extra new Lagrangians, and then do Lagrangian field theory with the standard techniques from there. Very beautiful, but not what I want to do. At the moment I want to do something which I think is more powerful. Right. So, force the underlying maths to parallel reality as closely as possible, find the axiomatic basis, and go for it. So, yeah, that's it, that's fun. So what is the quantum bicycle that I'm talking about, that I've been talking about all this time? Quantum bicycle is the underlying structure of a quantum particle, how quantum mechanics works. And the reason we call it the quantum bicycle is because of a partial analogy of what would happen if one were to imagine oneself in space on a bicycle with big wheels. So you're sitting on a bicycle, you're wearing a spacesuit, so you're alive, that's good. You've got a big wheel, which is roughly the same moment of inertia as you have, and you start pedaling. What would happen? Well, as you started pedaling, the wheel would rotate, and you would anti-rotate. So if you'd spin in the opposite, conservation of momentum would give you a spin and an anti-spin. Now, take your bicycle, click in another equally massive wheel at right angles to the first one, and start pedaling. What happens? Well, you sort of do this kind of thing. Then on a third wheel, you can have a third wheel perpendicular to both, hard, and then that one as well. Now put cogs and gears in there and make those things harmonic. So some of the wheels are going twice as fast. Some of the wheels are have twice the moment of inertia of others. Travel half as, or alternatively, you have them in different ratios, factors of 2 ratios. So one of them goes twice as fast as the other 2. Then these kinds of analogies, although they're only partial analogies because you're in 3 space, and we're going to be in a much more complex space, are partial analogies.
Can I interrupt you on this point?
Certainly.
Your quantum bicycle
Yes.
is always, no matter how, if all the wheels spin in the same...
In 3 space, you're right.
In 3 space, at the same rotational speed, and you are counteracting that speed. In my opinion, all you're doing is, where you were originally in this plane, you put the other one in, you're still doing a circle in this plane.
You are completely right.
And you will always stay in a circular motion.
Anton, you are absolutely right. I give that to you 100%, but I'm going to be in a 16-dimensional space, where I can put the wheels in different spaces. That would happen.
No, that's okay.
That is good thinking.
Yeah.
Good man.
No,
Yes.
so now I've been through that exercise.
Yes.
That's why I know.
I know you know.
And
I give it to you straight away. You're absolutely right, because all that happened, as we know, is the 3 angular momentum vectors will add vector with it. So it's only a partial analogy because, anyway, never mind. Let's do the real thing, not the pretend stuff. Right. So, the question is, what are wave particles made of? So what we're going to talk about, the best usual mainstream theories, you tend to use a complex wave function. So you have something which is real imaginary, a part that squares to positive and a part that squares to negative. But the complex algebra is commutative, and reality is three-dimensional, it's non-commutative, it's sometimes anti-commutative. So, in my view, merely complex is likely too simple, though it may be part of the story. So, the underlying base of reality, if I'm putting it in at the base level, is going to be a non-commutative algebra. If I put space and time in, the space part of that's non-commutative. And I'm going to do that. I'm going to take the hit on that, because you can. So, I think the physical wave function should be represented, physical as in real wave functions in real space and real time, should be represented by four-dimensional systems which are non-commutative. And I have developed an algebra which allows me to handle that kind of thing, which I'm going to show part of just now. It's relatively difficult. How I brought that in? I brought it in by noting something. My career to date has started out as an elementary particle physicist, quantum electrodynamics and quantum chromodynamics. I then moved to be a quantum mechanic. And in quantum mechanics, you have real imaginary wave functions, no real imaginary part. But to get the probability density, you square it and integrate over that probability density. So you do psi star psi, integrate over all space. That gives you a probability density of something stationary. If not, you bring in time, it gets a bit more complicated. That's the thinking area I went through. So, so the wave function is like a square root energy density in that sense. But also the electric and magnetic fields are like a square root energy density. The energy in the electric field, you do half times epsilon E squared, gives you the energy density in the electric field, and to get the total energy, you integrate over that. So the electric field is like a square root density. And so is the magnetic field, that's C squared, B squared, half epsilon C squared, B squared is the energy in the magnetic field. So these are all the things we associate with energies. The root thing is literally a root. It's a square root, mathematically a root. So I put these things in as roots.
Can we define wave function?
We will do very shortly when I write out the maths of the wave function. So fields are usually envisaged in 3D, but in fact, properly, a field is literally a derivative. It's a four-vector, so you can get the fields by taking the four derivative of the four potential. So they are literally derivatives. They're something which is defined both as a flow in one direction compared to a change in a perpendicular direction, that's a magnetic field, or a flow in one direction compared to a change in time, that's an electric field. There's something divided by something else. Space divided by space, magnetic. Space divided by time, electric, in terms of standard, well, tensor electromagnetism. So they're not really vectors, and we sometimes, a lot of people think this, and actually I think both the Hastings group and the Cambridge group have blown their brains apart by thinking they should be vectors, and everybody thinks they're vectors. So the Cambridge group does something called the space-time split, where they at this point project everything onto vectors, and I think that's, you've just sunk your boat, forget about it, it's not going to work. And Hastings is brilliant, one of my heroes, but he also doesn't put the physics in correctly in my view.
Or in mine.
Good. Okay, well there we are. Good.
And the Cambridge
support. The Cambridge group are nowhere. Forget about it. So they.
No, I've got nowhere with them because they.
Yeah, they
haven't.
They can't do the physics. They can do the maths, but they can't do the physics. I've talked to them too. They just. Yeah. Okay. We agree. Forget that. And I've tried talking to them.
It's sad. I thought that
it's sad. They should be good.
Yeah.
Anyway, but never mind. So one needs a field. One needs a theory that treats field and material on the same basis. So let's just do it, because otherwise I'm not going to get very far. Am I doing? Yeah, I know. I need to move on a little bit more quickly. So I'm going to talk about the fabric of space-time almost literally here. One often talks about the fabric of space-time, but I'm not going to say that this is space and time. I'm going to say it is like it is. I'm going to keep that open because we could have a space-time flow embedded in a space-time matrix. So there might be dual, there might be... But all I'm going to put in is the maths of the space-time and see what comes out. And I'm going to say, how can energy be conditioned into space and time? And what I'm going to talk about is I'm going to talk about energy occupying vector x, vector y, or vector z, or vector t space. So a flow of some description, call it a vector potential, that's probably the closest in x, y, z, t, four vector potential. But then I'm going to think about that thing being able to form also in a linearly independent xy space. yz and zx space as planar forms. So imagine you have something which is already a vector and it's varying sideways. That's an aerial form. It's a plane form. It's a bivector form inside a Clifford algebra. So I'm going to do the algebra of real lines, planes, in 4 space, volumes, 4 volume, a hypervolume, and also the scalar point. Now this is a point as opposed to a line or a plane, not a point which is something which is virtually not there at all, not what's often called a mathematical point, which is an infinitesimal point. It's a point in that it has the point property of being the scalar element of this algebra. That's all. Whereas you also have a vector element, and you have line, you have aerial elements, you have volume elements. In particular, the scalar point can take any energy, just like any other vector component. I have as much xness as I like, but I can have as much mass as I like as well, as much mass energy as I like, from 0 to whatever. No limit. So this is, we're used to thinking of points as being points, but you can think of a point as being a very short line as well, or a very small area, or you can think of it being an overlapping thing. This is just the scalar element of the algebra. This is no more than that.
And of course, that's exactly how people thought in the 17th century.
Yes.
Arrows, notion of linelets and linelets.
Exactly. Yes. Yes, exactly. So that's what we're going to do. That's what I'm going to do. So I'm going to develop a process which is designed to solve the extended Maxwell-Dirac equation. The equation I'm going to solve is this one. It's dg equals 0. So here, this is a bit of a joke equation. Everybody can do this. You know, the entire universe is called G. There's some differential function, and the answer is that the rate of change of the entire universe is nothing at all. But it's not entirely a joke, unfortunately. Not unfortunately. Fortunately, that is pretty much the way the universe works. But nonetheless, that kind of equation raises 5 things immediately. What's d? What's g? What's equals? And what does 0 mean in this context anyway, right? So that's all we have to do. That's the details. So what's the material? What's waving in? What's g? What's the vector differential operator d? What's 0 in this context, and what's the equality? That's the things. But also, I have actually been a little bit disingenuous in saying there are only 5 things in the theory. There's also an algebra. We're also going to put in a mathematics. And that's very important. So not only do we have elements, but we also have axioms. So what are those axioms? And one of the axioms is going to be dividing space by time. What does it mean to divide a ruler by a clock? What does that mean? I mean, okay, divide 6 by 3, 2, fine, that's a number. But when you're dividing something by something else, which are parts of the same 4 vector, that's a non-trivial conceptual thing. And we're using a mathematics to describe that. Well, the question is mathematics up to the job at all? Maybe not, but I'm going to try and do my best. So what's going to be different to what other people have done in this? In Dirac or Maxwell? Well, I'm going to introduce 5 and only 5 degrees of freedom to begin with. So I'm going to strip the Clifford-Dirac algebra to the bone. And in particular, I'm going to take gamma 5 out of it, or the complex part out of it. So I'm just going to use gamma 0, gamma 1, gamma 2, gamma 3. I'm just going to use 0, 1, 2, 3 for that thing, for those cognoscenti who know all about Clifford algebras. So I'm not going to have the gamma 5 in. I'm going to bring it in a different way later. But I've also got the freedom to introduce it at any time. And that's nice. So I'm going to see how far I get without it. I'm going to absolute relativity. I'm going to make addition, multiplication, and division, whatever they are, correspond to process in nature. So in particular, the multiplication of a 4 vector is going to give me a 4 Lorentz scalar. So I'm going to define multiplication so that it does that, as it does in nature. So I'm making the definition of my axioms get as close to nature as possible. And in fact, if I'm absolutely ruthless about this, I don't even really need multiplication. I can get away with just division. And I don't need addition. I can get away with just division. But I don't do that because I do use multiplication later on. But one could devise a mathematics where addition didn't work, or it wasn't necessary, was not required. Now that doesn't mean, remember we were talking about this with Roger as well, it doesn't mean it's not there, it just means that one doesn't need it for this specific thing that I'm going to develop. So, right, let's just do it. Okay, so what are the objects we're going to talk about? They're linearly independent. There's the vector things which generate the algebra, alpha 0, I'm going to call them alpha, not gamma, just because the alpha p doesn't act like the number 1, which I put in the Clifford algebra entirely. So alpha 0 and alpha I are isomorphic to the gamma 0 and gamma I. I have used that too. I've had a couple of slides where I use gamma. The 2 things are the same symbol. I'm using alphas. So alpha 0 is a unit vector in time, alpha 1 is a unit vector in x, alpha 2 is a unit vector in y, alpha 3 is a unit vector in z, or any other proper orthonormal, conformal coordinate system, toroidal, sphericals, whatever you like. It's a triple of perpendicular unit vectors. So alpha ij is the Romans are 1, 2, 3, and the Greeks are 0, 1, 2, 3. So that's my indices. Alpha ij is alpha 1, 2 is x times y, 2, 3 is y times z, etc., etc. These are the unit areas. There are 3 unit spatial areas: x, y, y, z, z, x. But there are also 3 unit temporal areas: x, t, y, t, z, t. So there are 6 of those objects, not 3 and not 4. Now, if you think about it, this has always been the case for such things as the electric field. There are 3 components of the electric field, not 4. It's not a 4 vector, and it never was. The electric field is not a vector, and it never was. Vectors in 4 space have 4 components, not 3. The electric field's got 3. Always did have. So this is what I mean about not thinking clearly. Some people go, oh, the electric field's a vector. How do I know it's a vector? Because I read it in my favourite textbook. That's bullshit. You're just not thinking straight, thinking the electric field is a vector. It's a bivector. It's an aerial element. So, other things I'm giving names to, alpha 1, 2, 3 is the unit directed volume element, so it's a volume which can be either outward directed, the hedgehog, or inward directed, the painful anti-hedgehog. So that's a directed volume. Alpha 0, 1, 2, 3 is the directed we call it the quedgehog because it's a 4-dimensional thing. So it's a hedgehog in 4D. And alpha p is the most important one here, which is the scalar unit. It's the most important new feature that's going to happen. So everything's made of what's waving in space and time. Root energy density folding and unfolding. So if you've got something which is a vector and you hit it with a differential, you're going to get 2 components. One's going to go up to an area, and the other one is it's going to go down to a scalar. So there's going to be 2 elements in the full product. Any product is going to go, so if you start out with an odd index, with a single index, and you hit it with a vector, you're going to get 2 even ones, no index at all, and a double index. So if you've got some energy, the way that the dynamics of this thing's going to work is that energy unfolds from a line to a plane, or folds from a plane to a volume. Equally, it can fold down from a volume to a plane, to a line, to a point. So the fun that energy can have here, energy can exist in 16 forms. What are the 16 forms? 4 directions, 6 planes, 6 volumes, x, y, z, y, z, t, z, zx, t, etc. And 1 scalar and 1 quedgehog. 16 linearly independent unit elements.
Are these objects differential form?
Are they differential forms? No. But they're closely related to the algebra forms, but they're not themselves. It's a wider definition than the algebra of differential forms. So yes and no. Yeah, partially yeah. Same sort of things. So I've called, it's a bit silly actually, I think I'll take this stuff out. I've called these things VOT, as in VOT is the matter, what is, so it's a bad...
What is your name?
Exactly.
The joke.
So because I call this stuff pivot, I decided I call the stuff pvot, and then I call the vector stuff vvot, and the bivector stuff bvot.
So these are
But it actually annoys me myself, so I'm sorry about that. Don't forget about that. Don't even call them that.
These are the dimensions of energy.
These are the dimensions that energy can. These are the forms that energy can take. Energy can take the form of being a vector energy or a scalar energy. Now, the nice thing about the algebra is that if you define the 4 vector which generates the group as having the Lorentz transformation properties, then everything else does exactly what you want. Anything that's scalar is invariant. It's an invariant mass term. The vector transforms as a Bohr vector. The bivector transforms exactly as the electromagnetic field. The trivector transforms like an angular momentum. So every single thing fits into place because of the definition from the axioms of a full Lorentz algebra. You don't put it in, you get it out.
Is the Lorentz algebra the only one we see in physical experiments?
I would argue yes, but I don't know if I'm right or not to say that. So I'm going to develop a first order relativistic theory of the dynamics of that stuff in space and time. by defining a 4-vector derivative. So you define a 4-vector derivative, and this is the definition of the 4-vector derivative here. There it is. This thing just here. So specifically, it's so derivative with respect to, let's say, x is you divide by a little bit of x, which you make a discrete derivative, make it small, and then allow the thing to go to 0. But also, absolute relativity doesn't allow you to put any xness in there without putting an alpha x with it. That's the point where you put the absolute relativity in. So define that, then what, to your utter astonishment, if you define the vector derivative like that, and you find the fields to be d mu of the vector has a form which is a bivector form, and then do the derivative of the vector, then what you get is you get exactly the form of four Maxwell's equations, just and no more, with all the right signs. In other words, this algebra that I've created is isomorphic to the Maxwell's equations at the level of the fields. So that's what comes out. All 4 Maxwell's equations, correct sign in a single step. But I'm going to do more than that, of course. What I then do, and this is the new theory. So this is the central side of the new theory. Here is what I'm going to do. I'm just going to do the 4 differential of the 16 components. 16 components are lines, planes, volumes, hypervolume. So then you just do it. There it is. All those. But if you start, so that's the theory. And then you say that whole thing equals 0. So each term separately, each of the 16 equations here is separately equal to, each component is separately equal to 0. Gives you the dynamics of the new theory.
Is that whole thing G?
G is no. This is dg. G is yes, yes and no. Yes. This is each one of these. This whole thing is a set of components of G after the first differential.
Okay.
Before the first differential, so if I just took phi G, I have alpha 0. If I just took psi G, I have alpha 0, psi 0, alpha 1 to 3, psi 1 to 3, alpha 1, psi 1, etc.
Okay.
But then going through the differential, you get this bunch of cross terms.
Wow.
But if you look at the terms, you see they have exactly the same form as you're familiar with from three-space algebras. So you can make a mapping and you can translate that into standard three-space algebra as this set of 4 equations. But this is a translation of specific Lorentz frame. So you end up with your Maxwell's equations, the first 4, with these P. This is what I went through in the first slide. And you end up with these. And then this second set of equations, the ones in, I've left these things in explicitly, but of course you can divide them out. The ones in the even set, the even resultant, that's the odd set for the derivative. This 4 derivative of the odd set gives you an even set, and they give you angular momentum and quantum spin. So they couple angular momentum and quantum spin. So, now, I'll skip over this because I'm running short of time, but except for one thing, what one does, everybody talks about 1 over the square root of 1 minus b squared over c squared as being relativity. Relativity really comes from the relationship of E equals h nu. And if you look at the relativistic Doppler effect and take the ratio of the wavelength of light or the energy of light as being r, then you can derive these things from that ratio r. So r tells you how much energy there is in your light. So if I take some light and I shift frame so I'm almost co-moving with the light, light is massless because as I get closer and closer to 0 energy light, the thing goes to 0, well, it goes to 0 energy, it goes to 0 mass with this ratio r. So and you can derive the 1 minus the range things from these as 1 over the square root of b squared minus c squared is a half of r plus 1 over r. So if you've got light in a box, then the stuff co-moving and you move the relation to the box or move the box, then the light is transformed and it's travelling in any direction as Martin showed in Vigier, but take it just for simplicity travelling in the x direction. The light is blue shifted one way and red shifted the other way, but it gets more energy being blue shifted than it does getting red, because it can only have 0 in red and it go up to infinity in blue. And that combination is exactly the Lorentz factor. That's where it comes from. So there's a deeper level of relativity than the 1 over square root of b squared minus c squared, which comes from this hot crap. If you just look at the wavelength of light and the way the light transforms, you can derive it as well, better.
So is that R not what's in what we conventionally with the R is what we found out?
That R tells you what the wavelength of the light is. So any specific photon, so you have a sort of master photon, and then all photons follow the same thing. Now, forget about Louis de Broglie, who was a very nice man. I want to get on to wave functions. So what we need to do is to define a wave function in absolute relativity. And the wave function, if I'm doing an absolute relativistic wave function, I'm not allowed to put x in. Here's an x, here's a z, sorry. Z's unit vector in z direction is alpha 3. So I'm not allowed to have even an exponent that doesn't contain a multivector quaternion-like element, in other words. So there it is, there's my alpha 3z, and there's my alpha 0t. And that doesn't work as a wave function, because while time in a plus minus vector x squared, while space squares to -1 and supports oscillations in the standard way of expanding an exponential, time doesn't, it squares to +1, so that gives you a falling or a rising exponential. That's not a wave function, it's something that decays off in time. So we'd either describe something exploding in time, the Big Bang for example, or something decaying and vanishing in time, which things don't do. I mean, look at persistence. So that's no good. But you can fix it by analogies to complex number transformation of e to the x goes to e to the ix gives you a travelling wave, by finding an element of the algebra which transforms both of these into things that square to -1. And such an element is, there are 6 possible elements that do that for this specific thing. But perhaps the most interesting of these is a unit vector in the angular momentum direction along the direction of travel. You require an angular momentum with this thing as well, or a unit angular momentum along the direction of travel, which is an invariant under the transformations in R, which it is also in the mathematics. So the mathematics parallels reality. You require something which has that form. Now this also, although it's a wave function, it's not a photon wave function, because it contains 4 elements. It contains 2 phases, one in space and one in time, and it contains 4 elements. It's a mass field wave function. So while it's not a wave function of a photon, it's a candidate element of a wave function of an electron. Now, why it's so important is this thing has an astonishing mathematical property, which is if I multiply it by a field, by an electric and magnetic field perpendicular to one another, any field, any magnitude, what it does is, provided those fields are perpendicular, it takes them and it propagates them. It turns the entire thing, the mass bits cancel of the whole thing, you're left with just field, and the whole thing propagates in the direction of E cross B, Badoom.
So that's where the ion in it, or that's a volume element?
There's no I in it. If I multiply this thing by 2 things which correspond to an electric field in the x direction, alpha 0 in one direction, and a magnetic field, alpha 3, 1 in the y direction, then the whole thing then that thing is a propagating form, which is a solution to the Maxwell's relations alone. In other words, d that is 0. Four derivative of that thing is 0, which is easy to show. So that's a photon wave function, but it contains this parameter r in 2 ways. One of them it contains the exponential, which tells you how the frequency is modified. So it says the frequency is related to the energy. It says the angular momentum is constant, because if you calculate the angular momentum properly, r doesn't change the angular momentum, it makes it bigger, but it has less energy in it. And so this describes every photon, each and every photon, the same photon in any frame. As r goes to 0, the energy goes to 0, the frequency goes to 0, the photon goes to 0 energy and 0 mass. You can take r up to whatever you like, gamma, whatever you like, same thing, just different frames. And a single parameter r. So it's a photon relativistic wave function. There it is. So this is, and if you then take the fields and look at them, what you get is you get the solution you'll find in any classical textbook of electric and magnetic fields just circulating through time. If I can decompose it like that. So it's a photon because it matches the experimental properties of the physical photon. It's quantized, well, at least it's a constant angular momentum, and it propagates in the direction of magnetic handedness. If you change the magnetic handedness, it doesn't propagate. It frequency doubles. So it only propagates the thing you see for physical photons. If you change the handedness, it propagates in the opposite direction. That's a solution. You have to reverse time to get a solution. Anyway, so the quantum. Anyway, right. But what I want to get on to, and I have 30 seconds left, so that's perhaps not very clever, is adding the mass term back in. Now, this is perhaps one of the most important slides of the talk. So, if you add the mass term back in and calculate the electromagnetic momentum, energy momentum, then you get So this is what I've done, is F is the 6 components of the magnetic field, and P is the mass, is the rest mass term. So F dagger would give me, F dagger is the Hermitian conjugate F, would give me the standard expression for electromagnetic energy, E squared plus V squared, and the Poynting vector, E cross B. Sticking P in modifies the energy by putting an extra mass term in, which goes in the same way, but look what happens here. E cross B is perpendicular to E and B. What comes in as a term which is perpendicular to E cross B in the direction of the electric field modified by the mass. And what that means, it means that in the presence of pivot, light pivots. The momentum no longer goes straight forward, but it also turns perpendicular to the electric field. So I'll show you how that works with a model. So if we take a model of light, and this is also related to the yaw factors of half one and half in ordering, as I'll show later. But if we take a single wavelength, so I'm imagining the electric field is outward directed on the shiny side of the belt, and the other side's got some writing on, so you can tell the difference. So there's a single twist in space, whole wavelength. Now if I move that up half a wavelength, that would destructively interfere at this point, because that's downwards and this is upwards. So if I move that half a wavelength, that would destructively interfere in normal space. But if I do what we did in this 97 paper and I form a single wavelength loop, which is this, then the very phase on going around the loop introduces an extra phase factor, which means that at the halfway point, the two electric fields are in the same direction. Extra factor of -1. And what that does for you is it means the whole thing's resonant, coherent, harmonic, and non-interfering. Also, look at it. Field's outward directed everywhere. It's charged. And you can calculate that charge, and you get the electron charge. Not only that, you know that it's a photon, h nu. You know it's going around in a loop. You can size the loop's lambda c over 4 pi, because it's a double loop. So you calculate the spin, it's h bar over 2. Not only that, if you take one of those objects and stick it into the same, try and put two in the same state, the fields will add. So you get double the field everywhere. Double the field everywhere is 4 times the energy, because it goes as E squared. So that doesn't go, Pauli exclusion principle. Turn it upside down precisely, half the fields exactly cancel. And it does go energetically, Pauli exclusion principle. Spin up, spin down, okay. Spin up, spin up, not okay. So that's a physical explanation for the Pauli exclusion principle, which also has a limit on the Pauli exclusion principle of twice the electron mass, which is also what's observed in spin polarized scattering. So if you go to hydrogen physics. So that, also, it's a physical spinner, look at it. You go around once, you're on the other side of the belt, you need to go around 720 degrees to get back where you started from. It's a physical spinner. But, that diagram, this diagram, there it is, it's not in space. The electron's not a donut whizzing around in space. The only things in that diagram are mass and bivector space, quaternion space, because the mass magnetic part is isomorphic to the quaternions. The dual mass electric field part is isomorphic to, well, it's dual quaternions. They don't act like quaternion algebra, they mix. Quaternion algebra is closed, this one isn't. But it's not in space. The electron is not a little loop in space, it's a little loop in field momentum space. In field space, what happens to it?
This is not a geometric.
This is not a geometric little thing going around the vortex. No.
It's more like a kind of geometric break.
It is. We're sitting in a different space. We're sitting in a 16-dimensional space where these rotations are taking place in different spaces. So the rotation's in a different space to space. If you project it onto space, then you can do that, and this is what you get. There you go. Just a minute. This is a 4-dimensional rotation projected onto 2 space. And so I wrote this applet to do this. So this is what it's doing. Then if you just follow that around, then it fills all of space. I can make it go faster as well. Okay, or we can make it do more things. Anyway, our kids play with this for hours. As you can see why. so but what it is, it's an enfolding. Well, okay, the projections of a hypersphere onto free space are toroidal and spherical. So you have both toroidal elements onto certain projections, but the projection down onto real space is purely spherical, and the electron is spherical in ordinary space. And I'm afraid I'm going to get stopped, quite rightly so. So what I'll do is go the other way. and go to conclusions. I was going to talk about forces. I'm sorry. I was going to talk about the uncertainty principle, exclusion principle. I did. I was going to talk about how quantum collapse works, but that's another talk. How it's analytic. Experimental tests I was going to talk about. There's a whole bunch of things I want to do, but I'll go to conclusions. New linear theory of light and matter. What it does is it extends Maxwell and generalizes the Dirac equation to look at matter and mass in a more sophisticated way. It has 4-element wave functions which act as pitches and catches of light, which can generate with any size of initial electric magnetic field configuration. They'll propagate it. So it's a mechanism for generating light from charge. It shows how charge actually works and the dynamics of charge. Extension with mass leads to charged, localized, half-integer spin objects obeying the exclusion principle. So I wonder what they are. We think they might be the electron and positron. So it also explains how the electron can do the incredible stuff that it does in getting very big in the solid state. I didn't have time to talk about this, but it's an important thing. The electron is not a size thing. It's not a size object. It's a topology. It's a topology. The electron can get as big as you like and remain an electron. In its natural state in space, it sees space, and that space shrinks it down to the size that you see in space. If you try and hit it, it bounces off quantum electrodynamically, but it's really a confined photon. So it scales in the same way that an exchange photon does, and it looks point-like. So it looks 10 to the minus 18 meters, it is 10 to the minus 13 in space, it is 10 to the minus 10 in matter, and it's whatever you like in the solid state, so as big as you like. That's how they work. And that's the end of the talk. Thank you for listening.
No more than one question.
It's been suggested that an electron can be thought of as two Majorana particles.
Yes.
In interaction. Do you have a topological picture of that?
Yes and no. That's a very good way of thinking about that. Do I have a topological picture of that? In a way, yes, but I'd not say Majorana, I'd say Dirac, first of all. And secondly, what I do, if I want to write down the wave function, which I haven't really got time to do, it's a bit technical, but what I do is go for the half-integer Legendre polynomials of these things, describing the two different spin states. So in that sense, a little bit, yes, but I wouldn't
so
go for Majorana.
In other words, you think there's a good possibility of getting a topological picture?
Yes, I do. I do think there is. I wouldn't go in Majorana, I'd go in Dirac, though. Because I think one of the things we're doing is we're looking at the different handinesses that you can put in at different signs, so we can switch between Majorana and Dirac inside the algebra. That's one of the things we do. And the Majorana thing doesn't work at the moment. But the Majorana thing, the stuff we're doing also has an implicit ordering, which is why I asked you about the ordering. So what we're doing is, if we have an object in differential, you can choose that if you're dividing an object by another object, you can either divide into it, you can go 1 over x times y, or you can do y times 1 over x. And when you're dividing, that order is, which order should you take? Now you should take both. So that's the other, and go into something like a commutator. And that possibility exists as well. So if we do a commutator on this, some parts survive in any given pit, and some parts cancel, as you know. So you have to do half of those. The parts that survive in this particular one are, for example, the Maxwell's equations, and the mass parts stay there under commutation for this Dirac algebra. But in the Majorana algebra, we run into problems, which we could talk about at some stage. When we sit down with it, it's certainly worth talking about, yes.
The other question is, back a few slides, you have the black and white picture of the belt. Never mind, you don't have to go get it. But that's from some paper of yours, no doubt.
It is, that's from a paper.
I had seen that paper before for a moment and not paid it good attention. So
well, I think
I'd like a copy of that paper from you, or if you have a
I should give you a copy. And also another thing is, I've given a copy of our unpublished vision paper. We have submitted it 3 times, so there are versions that we've sent to all the best places. Haven't got it out yet, but it's very technical. But it's exactly the kind of thing that would suit you down to the ground. I'll give you a copy of that too.
Sure.
Good.
So, okay, great, thank you.
Pardon?
Time for coffee.
Time for coffee, yes. Super.
Your space-time on route